Okay, so let's take a look at our example. Okay? Now this is the beam that is designed to sit on the concrete. So as we all know, we are going to have the reaction here, and the reaction will act as a point load that may cause the beam to fail under the local failure as well. So we now know that if you have a case like this, you must investigate all the possible failure modes. Okay. So in this case, this W is the uniform load, the date load of 6 tons per meter and live load of 9 tons per meter. The condition for design is that the depth of the beam cannot exceed 250 millimeters. So you may, face a situation like this in your real life. Maybe something happens, you need to add this beam later on after everything has been decided, and you are left with just this much depth. And also a condition of the deflection due to live load should not exceed L/360. We are going to use the SS400. It's the same thing. And the concrete FC prime is 240. It's a basic number. The span length of the beam from support to support measured 1.8 meters. Okay, and this beam will sit on the concrete beam that is 250 millimeters wide. Okay, that's the width of your beam in this direction. Okay, so now because somehow this is the example that I took from my class a long time ago, and I had a lot of stuff going on with RFD because they were just promoting it. It was new when I was there. So let's say if it's a factor load, we have to check two load combinations. First is pure date load. The second is date load plus live load. So surely this is one is going to cover. So this is RFD, right? When you use RFD, you must do this. But if it's ASD, you don't have to do anything. It's a service load. And from this, we can calculate the ultimate shear, basically WL/2. Okay. And 4 is WL²/8. So we just multiply that. Okay. And again, just like the example that we had just a week, I was going to say that. We're going to have to assume the section is compact first. And from that, we know from this, it's mu cannot be greater than Fy, Zx, and then phi. Okay, phi is 0.9. So now you can, mu is 8.75 ton-meter. So the Zx will have to be greater than 8.75, which is mu, right? Multiplied by 10 to the power of 5. And then divided by, you move this to the side, 3.9 and then Fy. So we get 389 as our minimum required number for our plastic section modulus. We go to the table, and this is what I plucked out of the table. H250 by 175 by 44.1. Okay, it may not present the best option, but remember that we are limited by the depth. You can go back and try to look at the your steel table by plastic section modulus. We want 389 here. So you can use this, you can use that, right? You can use this. Let me erase from last week. You can use anything because it's 389, so you can use anything going up there. But point is, it's only this one that fits the depth criteria. This one will exceed the depth criteria, and this is the column section. Okay, so it's not a good idea to use this column section, but besides they are heavier as well. So we are left with this. Okay, so we go, we go back here. We try this section. And I plug out the ratio. This is the flange compactness. It's 7.95, which is less than our limit. Should have written down 10.8 maybe. That's point. Remember, it's this is 0.38 square root E over Fy, right? And that's 3.76 for the web. So flange is compact, web is compact. So your design moment, which is VMN, is basically, well, I got this number from the old table, which is in Newton meter, and I divided by 9.81 to change the unit. But alternatively, this can come from basically 0.9, 2500, and then multiply by the shear for this guy is which one? 558, right? Yep. This is the number 558. Then divided by 10 to the power 5. You get this number, which is greater than our required moment. That is okay. That is done and over with for the bending moment. Now we move on and check the shear. Okay, and again, we need to investigate the local buckling. The slenderness ratio is 27.1, which is less than 70.3. That is 2.45 square root E over Fy. Okay, so you have a compact section and your shear is simply I took this from the table as well with the 9.81, but alternatively, again, you can calculate this from 0.9, and the shear stress is 0.6 multiplied by Fy and multiplied by the depth and the width of this, the depth and web thickness, this section. So let me try to find the number, not in here. So this one. Okay. That one. Let me erase the old stuff. All right. So it's this one. Okay. Depth 244 and T web 0.7 millimeters. So here is 24.4 multiplied by 0.7. We divided by 1,000. You got tons, and then it's going to be close to this, but it's not an issue, so we are fine. And the next one is the serviceability criteria, which is the deflection. Again, we have to be limited in the elastic behavior. And this is the formula for elastic: 5 over 384 multiplied by the live load alone, which is 9,000. Again, I change the unit. I multiply the uniform load with meter and then leave the L cube in centimeter. Okay, we forgot to bring this up and divide by 384, and that's that too. Okay, so essentially it's, let me rewrite this, 5 over 384. And this is the uniform load in kilogram per meter multiplied by the length in meter. That becomes a load. That's 180 left in the cube over E, which is 2.04 multiplied by 10 to the power of 6. And then I of the section, which is 6120. It's 0.1 centimeter, which is less than our limit, our let's say required design criteria for this project. So we are fine. Okay. Now it's time to design another stuff. Now I got the number right down there. So let me show you the calculation. Okay. Now because right here, this is the where your base plate is, and your load is now going to be at the distance 5 centimeter. Okay, let's say I call this x equal to 5 centimeter, which is less than the depth of 25 centimeter, right? And in fact, it's also less than d over 2. So yielding, let's say that's for yielding. Yeah, that's for yielding. That's for crippling. So we fall into the category where we say the load is too close to the edge of the beam and our strength will be reduced. So check web yielding, that this guy comes from when we are at near the edge, the phi is 1, right? Now we have 2.5 K instead of 5 K. N is 10 centimeter plus 2.5 K for this. You can go to the table and see K here, right? Oops, shouldn't have done that. That's K and it's 27 millimeters. Okay, so back to, oh, I'm sorry. Yeah, back here, this guy is going to be 2.7. Okay. That is your K, and then the thickness of the web, I just got it a moment ago, it's 0.7, right? Multiply by 2500. If you divide it by 1,000, you get the number in tons. Okay, so that's exactly how it comes from. The web crippling, now because it's in the edge, so you must check the N over D ratio before you can select the formula. All right, so N is 10, D is 25, that is about 0.4 maybe. It's 0.41 greater than 0.2. So you are left with this formula. Go back and try to find it for you, not here. There, the second one, okay? Pretty long one, and you have to be careful not to mess it up when punching the calculator. Okay, so this is 0.75. Let's use the wing. Where did I get that from? Hang on a minute. 0.4 t squared. T is 0.7, right? And where does that number come from? Okay, anyway. 1 plus 4, okay, and then, sorry, it's difficult for me too. Okay, here you go, it's a 4, it's in this. Multiply by the ratio of 0.41, right? So N over D minus 0.2, so the number from the formula, and then the ratio of the web thickness and the flange thickness. The power is 1.5, be careful. And then you're going to have the square root of E, let me shorten it. And then this guy is going to be flange over web. So swap that. Okay. Oh, it's not E, it's Fy, isn't it? E and Fy. So let me try to squeeze this in. Let us do it again. EFY and then 1.1 over 0.7. Okay, so that gives you that number, hopefully. Okay, and divided by 1,000 too. I'm running out of space. All right, now let's move on to the concrete crushing. Now, let's say the width of the beam. Now we use H 125 by 250, right? So this is the width here is 175 millimeter or 17.5 centimeters. So we're gonna try the 20 centimeter wide plate. So this essentially is the same as the thickness of the width of the beam, right? See, we have this. Okay, the limitation that okay, actually it's 250. So we're not going to use all of them. Let us start from 20 centimeters and see what happens. So your A1 now, okay, becomes 20 by 10. So let's say I'm going to try to draw this. Say this is your concrete beam. And this is your steel. All right, I should have drawn this from the beginning. What I said before that was not quite accurate. So to show that this is your steel, let's show the dotted line for the width of the beam. Okay, and this is going to be the plate. Let's use a different color for the plate. Here. Okay, now we use n equal to 10. So that means in this distance, it's 10, right? And now we assume that we're going to use the size of this equal to 20. And that is our concrete beam. That will be the support of this steel beam. Okay, so let me paint something. Okay, that becomes the concrete beam, and now you have the steel plate acting on it. So that is a steel plate underneath your beam, and this is going to be the the width of your concrete beam, right? 25 centimeters. And we are saying that we are going to try to use this 20 centimeter. So that is 20. And that is 10. Okay. So now the question is how much or how big my A2 can be now that my A1 is 10 multiplied by 20, right? You can see the A1 is this pink area. Okay. But now in order to have A2, I must project this and make sure that my A2 area is concentric with the A1. So if I put it like that, you know, if the width here is 10 and the width of the concrete beam is 25, it means that I can go to the side 15.5 each, right? Can you see that? I can go with this distance equal to 7.5, and that is also 7.5, correct? So 15 and 10, so that's 25. So to make this concentric, sorry, I need to move this a little bit. Now let's erase that. Let's try to make this shape, say, more practical. Okay. All right, this is my concrete beam. And I have to make sure that the A2 is concentric with the A1. So I can have this 7.5 out. That means this has to be 7.5 as well, right? If they are going to be concentric, this will go up 7.5. This too will be 7.5. So now that is going to become my A2, limited by the edge of concrete beam. Okay, I'm going to use the yellow again. So that's my A2. Okay. Anybody has any question? So A2, you know, on this dimension, for the width, A2 is, yeah, 25, correct? Has to be. But for the vertical dimension, the A2 will be 20 plus 15. So that's 35. Okay. So that becomes your A2. Is there any question about that? Well, no. But again, we have to check the limit. And the square root of A2 over A1 is greater than 2. You can see because 4A1 is 800 square centimeter, right? Now you have A2 greater than that. So voila, you cannot go beyond that. And therefore, from the formula, which is this one, let's see, phi is supposed to be 0.65, isn't it? Make a mistake. Yeah, from 0.65, my apologies. So this has to be, that's wrong. Okay. So it's 0.65. And then 0.85 multiplied by FC prime. And then the area A1 is 200. Now, because the square root A2 over A1 is greater than, oops, square root A2 over A1 is greater than 4. So you are limited to using only 4 for this, and this becomes 2. Okay, that divided by 1,000 will give you hopefully the number. I forgot my calculator, so if you could, can you punch that for me? Get the right number. Hello, anyone? Can anyone help out? Oh, no one. Well, so let's say I can't confirm that number and I forgot the calculator. My phone, you can, yeah, get my phone. 1 second. Okay, so hang on. This is going to be 0.65 multiplied by this.
I got 53.04.
Yeah, 53, right? I got 53 too. So I got 53 tons. Let's say 53 tons. Okay, so which is safe because our reaction is about less than 20 tons, I remember. Here, it's 19.4 tons. So here we go. It's safe. And now we know the size. Okay. In fact, you may, you know, in theory, now we use the size of the plate that leads to the A2 being more than 4 times A1, that means the size of the plate is slightly too big because it doesn't give any benefit, correct? If you want to know, you can try to back calculate by setting up this equal to 2 and try to get the area A1, right? And when you get A1, you can convert that into the dimension of the plate. So let me take this note down for you. The fact that, oops. A2 is greater than 4A1 means the size of the plate is too big. To get the theoretical plate size, you can set up the equation to your load is 19.4 tons, right? Say, can it be greater than this? 0.65 multiplied by 0.85 FC prime, and then A1, and then multiply by 2, right? Divided by 1,000. And now A1, because you use n equal to 10, so you can get the width, okay? But maybe you get some number that is not round. Say, but if it's slightly less than this, maybe 18, that would be like a nice number to have as well. Okay. So anyway, let us proceed with this size, and you see that now we know the size. It means that we can now calculate the uniform load that will act on this plate, and we can design this plate as a beam. So now you have the load, 19.4 tons. You have the size of the plate, 20 by 10, correct? Don't be confused, be focused on what you're doing. The A1 is the area of the plate. When you design the concrete crushing, you have the factor to help increase the load carrying capacity of the concrete, because it's not going to fail at A1, it's going to fail somewhere deeper. But when you come back to the plate, it's now the plate area. So this divided by the actual area of the plate will give you the uniform load. And N here, because it's 20 centimeters wide, half of that is 10 and then minus K. So the cantilever length of the plate is actually 7.3 centimeters. Okay, and again, I use this formula, or you can just come ahead and use this one, where you have the uniform load and you have the cantilever length, and it gives us the thickness that you have to choose. It's 2.15, and so I decided to use the 25 millimeter thick plate. Okay, I can go maybe smaller because it's only 2.15, right? You can use 2.2 centimeter, 22 millimeters plate, but I'm not sure about the availability, so like I said 25, that's fine. Okay, is this too quick for this portion? You want me to go into details maybe?
Yeah, that would be great.
That would be great. Okay, so let's see if we can squeeze this. Okay, so to keep with that, the plate dimension is the plate dimension that we use is 20 by 10, right? Okay, and now we know that the total load that comes on this one is 19.4 tons. So now you can calculate the uniform load. It's a load per area, correct? So the FP, or the load per area, is 19.4 divided by 10 multiplied by 20. So that gives us the uniform load of 97.2 kilogram per square centimeter. Okay, but now our model of the plate as a cantilever beam, the plate is not going to bend from the center line, because right here it's considered solid. So the bending of the plate will begin at this critical section. Okay, and this critical section is just the distance k away from the beam center line. So this distance is 20/2 minus k, which is 2.7 centimeters. Okay, so that's you get. Can't see anything. I need to turn on the light. Just 1 second. Okay, so now it's the distance that we can use for the calculation of our bending moment, right? That becomes 7.3. Are you clear with this? Are you? No.
It's much better.
Okay. So this is your cantilever beam. Or let's use the pink one. But we are taking one, the strip of 1 unit of width. Okay. So you can see this now. And like I said, you can swap it upside down. So this becomes 97.2 multiplied by, because we take 1 centimeter of width. Okay, let's say 1. So you can multiply this by 1. And it essentially becomes the uniform load, 97.2 kilogram per centimeter. Okay. And then this is 7.3. So now your bending moment becomes 97.2 multiplied by 7.3 square over 2. That's your required moment, okay? And it cannot be greater than the strength of your plate, which is 0.9 Fy, and the plastic section modulus, which is the property of this section. Okay, so the property of this section, the plastic section modulus, B is 1, and then D is TP. That becomes 1 TP square over 4. That is the plastic section modulus of your plate. Zx of your plate. When you solve this, it's essentially that one. Okay. So how are we doing? Hello? Crystal clear now?
Crystal clear,ครับ.
Okay. Sounds promising. What about others? Senior, super senior, you okay? Okay. No response. Anyway, so let's move on to the last problem before the midterm exam. Now it's concrete column. It's the same, except that this time, instead of putting the beam on the concrete. Okay, good, Nodipong. Thanks for your response. I was waiting for you actually. Okay, you know you would. So we now put the concrete abutment underneath our steel column. Okay, so this time everything is the same except that we don't have the local web yielding and local web buckling. Now the base plate is like this. So you will have, instead of one cantilever length like the beam in here, now you have two from this and this. Okay, so now we are going to design this. I don't have anything here though. Check. Okay. Example of that is let's just say design base plate. How did I forget this? Design base plate. Oh. SS 400 and the FC prime is 180 kilogram per square centimeter. So that's like concrete mixed by hand, you know, it is so low. Okay, and say the condition that the abutment is so large that, you know, your A4 over A1 is surely going to be greater than 4. Okay, the steel column is this size with the ultimate load of 200 tons. Okay, that's the dimension of the column. So now we are going to check the concrete crushing to design the size of the plate that we need. Okay, and now we have the condition where the concrete is so large. A4 is guaranteed to be greater than 4A1. But now we know the limit is 2. So coming down to this, again, I got the factor wrong. Yeah, at one point in time I was confused, you know, it's concrete. Okay. So anyway, the phi is 0.65. All right, and we have 0.85. FC prime is 240. I'm sorry, 180. And the I don't know, A1, because we don't know the size yet, and then we're sure that it's so big that the factor is going to be 2, but that becomes that, and it has to be greater than PU of 200 tons. Okay, so with that we know the area of the A1 instead. Okay, so now with the area known, we can set this. Okay, coming from here, you know that this is, you know, the D, right? And you know the B, F of your column. So you can set this, the vertical distance N here is going to be equal to 0.95D plus 2M. You know, each is the cantilever length going above and going below here. And then the B, which is 0.80% of the width of the column plus 2N from the side. You can set this. Okay, now, you know, you have to design the plate thickness based on the cantilever length here, 2 lengths here. So if you make one way bigger than another, you're gonna be, you know, governed by the longer one, which is not the very good engineering approach, right? So in the theoretical world, you should try to make this equal, so that one, you know, isn't governed by another. So let's try this up. Let's say M and N is equal. So you know D, you know BF. So this equation comes down to one unknown, right? If you set the M and N equal. Or you can just try the size, because yeah, that's not a hard way to do it. Okay, so let's say after the calculation, now I know my real M and N. So I'm going to use the larger value to for my calculation. Okay, now 2 problems really. for the selection of the size of the base plate. One, let's say some students, when they calculate the size, you know, they would just say they use this size without going back and look at the size of the column. Okay, the size of the plate has to always be greater than the footprint of the column. Otherwise, you cannot fit it in. You can just look at this picture and you see that the plate will always have to be bigger than the column. At least, say, 1 or 2 centimeters on each side. Okay, another that it would be, if possible, don't use a size like this. It's okay, but if you can use the square plate, that would be easier for construction. All right, use the square plate. They don't have to worry about which side they need to, you know, rotate the plate to meet the end of your column. But this is to try to, you know, optimize the situation. So that's why we have a different size like this. And once you have the size, you can calculate M or N, and it goes back to the same design model here. Okay, because just like the previous example, once you know the size, once you know the size of the plate, wow, bends like that. Now you can calculate the stress, correct? So the stress FP is equal to 200 tons divided by 35, 31.5. So that's your stress. And now you have the 2 strips of cantilever beam, one in here and one in there. So you choose the one with longer length, okay, which is 5.62 here. And now you have yourself a cantilever beam, 5.62. This becomes a uniform load acting on it. Okay. Which is here, 181. Okay, 200 tons and divided by that area. Okay, so now you just go on, calculate it. The moment is 181, 5.62 square over 2. This cannot be greater than, again, this is LRFD perhaps, so it's 0.9 Fy, and the plastic section modulus of the plate, which is 1, and then TP square over 4. Okay, that's it. So yeah, pretty much we cover everything for the midterm exam. You guys can now design everything. Next Tuesday, I haven't posted it yet, but next Tuesday should be a due date for the design of the beam and the column. Okay, and say you can also design the base plate, but I have made a plan, right? I must look at that, because I may be able to give you an extra week to design the base plate. Okay, so here's the thing. Let me, that's the end of it. So let's stop the video first.